I'd been doing Puppet for years, like far too many years, and people said, don't reinvent the wheel. And like, this was the wheel that I realized Puppet was. Not to diss Puppet, but just tooling in general. But I do want to reinvent the wheel. I want this new shiny wheel, right? You want the shiny wheel? If you don't interact, you won't get any live demos. There will be no shiny wheel. So you better start. But so ultimately, I kept trying to find out, is there an existing tool that did all the things that I wanted, that was good enough? And I was trying to make Puppet be that tool for me. And so the question was, really, was there an existing tool that did all those things? Anyone? This is my answer to that. This is my Nope guy. I bring him to all my conferences. And he just nopes out. So long story short, after much, I basically sat down and started writing a prototype a number of years ago. It's called Mgmt. I have some stickers, so if you come up at the end, I'll give you a sticker if you promise to use it. And there's two main parts to the tool. There's an engine, and there's a language. I'm going to talk mostly about the language, but I'm going to show you just about what the engine does. So the language basically lets you describe basically what you want to have happen in your distributed system over time. So traditionally, tools actually expected and sort of assumed that your infrastructure was static. But we all know that our infrastructure is not static. Load changes, error conditions happen, all sorts of things happen every day. Maybe on weekends you want to turn down some of the servers. Maybe, who knows? So how do we program a whole distributed system that can react in real time? Now the engine has three main parts to it. Back from the language, just going to the engine. The engine actually does the work on your servers. It's a little daemon written in Golang that you can run if you want. And if you think of the graph of work that gets done, it does all of those things kind of like Puppet, except it can run the graph in parallel, and it can respond to events, and it works as a distributed system. So I'm not going to show you the first one. You'll just have to trust me that this thing runs in parallel really fast. These are the sort of graphs you have where you have different resources. That's these blue things of work to do, and the black arrows just sort of the dependencies. So traditionally, you would run something called a topological sort, and it would go through and do this red arrow and do the work. But an MGMT can actually do everything in parallel. So everything on the left can happen at the same time as everything on the right. And similarly, these red arrows can happen in parallel as well. Cool? Am I talking way too fast? Say yes? Oh, someone said no. You're brave. So I'm going to show you now. I want to show you the events. I want to show you a demo of that. And just to show you, let's see, is that big enough? Can you see? All right, just close this. So I'm actually going to run MGMT over here. I'm just going to run it, and I'm going to give it some code. I'll actually show you this code right here. I just wrote this little hello file. It looks basically like Puppet in some ways. It says there's a file resource, temp hello world, and has some content. I guess that's a surprise. So let's just actually run MGMT on the left. And on the right, if I go right here, you can see that very quickly, you can see that the file is actually what we expect, right? It created that file with those contents. Nice? It works. But here's the fun part. Watch what happens if I remove that file. It's right back. So if I remove the file and get it right back, it comes back right away. And the reason is because MGMT is actually watching in real time. It goes to sleep and it detects when the state of any resource changes and it will fix it. And it's actually so fast, I can even actually run remove and cat in the same line. And as fast, you can see it's actually going here, as fast as you remove the file, it puts it right back. Do you like that? Yeah, there's some people like, huh, what is this weird thing he's showing me? In fact, it's actually so fast, there's a watch command that will actually just run something over and over again. And even if I run watch over and over, and as fast as you can go, you can see the engine's waking up, fixing the file, and putting it back. Cool? Step one. So that's the events per resource. Now, we do this for all sorts of things. We do this for files. We do this for services, like systemd services. We do this for kernel, like exec commands. We have packages that we can detect when they're uninstalled or changed or whatever. And we can even do this thing for things like virtual machines. So we can actually declaratively set the state of a virtual machine. And if that machine were to crash, or if we wanted to change the number of CPUs or do anything like that, MGMT can make those changes declaratively on the fly in milliseconds. Cool? Sounds too good to be true, but I promise you it's not. So I think this is what I believe config management should be. It's a bit different from the traditional static config management tools that we're used to, but this is what I think config management is. But I also think this is another technology squished together into the same thing. I was going to say container, but that's overloaded. So what is this other technology that's also this? Does it feel like anything else to anyone? Scream it out. No. I actually think this is a bit of monitoring, right? So everyone who's actually ever put something into production, you have to do all your automation, do your config management, ready to put it to prod. Oh wait, you can't because it's not monitored. So if at the config management layer this is sort of built in, and you know that those services or those resources are going to be sort of checked, it's kind of like monitoring. So I don't have too much time, so I'm going to go pretty quickly. But basically, there's different topologies you can have. This is sort of like a typical client-server topology. There's a lot of problems with that. I won't talk about it. This is a central orchestrator. Has a lot of other problems, single point of failure, those sorts of things. You're all familiar with these? Just say yes, loudly. Yes. Especially the people in the back on their phones, just look up for a second, say yes, and then continue playing Angry Birds or cut the rope. Anyway, so what we actually do in MGMT is each machine, as it starts up, they actually form a cluster, a distributed topology, using something called the RAF protocol. It's a distributed consensus protocol. It's really cool. You don't have to know that it works. You just have to know that it's built into MGMT, and it does it for you auto-magically. Huh? OK. And the cool thing is if one machine dies, another one can take over. So what I'm going to do a quick demo of this. I'm going to actually just run on the left. I'm going to run a bunch of MGMT instances, one at a time. Now, these are all running on my local laptop instead of on separate machines, just because it's easier to show you what's happening. So I'm going to run the first one, and I'm just going to go into this folder here. And what I've done is I've written some very simple code that asks every machine to wake up, generate a random value next to its host name. So I'm host name 1. I want my random value to be blah. And I wanted to put it into this distributed shared database that's part of MGMT. And every other machine that starts up is going to do the same thing, and they're all going to exchange values. So let's see if I can just run a little watch. So I'm just running this watch command, which is just going to tail all the files right there. And you can see this first thing started up, and it just shows there's a map. So the first thing, it says there's only hostname h1, and it shows the random value that it generated. You with me so far? Good, good. So you want to see another machine? All right, oops. I just have this in Control-R. So here's my second machine. All you do, now you can look at this command line later, but all it does is I'm pointing it at the code that I want to run. That's this first part. All this is all the way, this is all free software. It's all on GitHub. You can even play with these exact examples at home, in the comfort of your home. I'm just giving it a host name because it's on my machine. And all I'm doing is I'm saying, look at the existing machine to cluster yourself together. So any new host, you just point it at any existing host, and it goes. Make sense? So let's run this. And hopefully it works. Boom, you can see very quickly the second machine came up. It generated a random key, and it saw the first random key as well. And the first machine, which is listed over here, noticed really quickly that there's now a new machine that has a new value. OK? While you're thinking about that, I'll just start up one more and watch what happens. Boom, now you have a third one. So the third machine started up, it generated a value, and now the other two can see that value as well. So what is this pattern actually doing? What this actually could be many things, but this could be the pattern where you have some load balancer, and as you start up new web servers, they just say, hey, by the way, I'm a web server, I'm at this IP address, I've got a service on this port, and the load balancer can say, oh, I see that you started up and you have a service on this port, I'm going to open up traffic to your port. And this happens dynamically in real time in milliseconds. So you can just have things coming and going and have your whole infrastructure just be very dynamic, putting data into the database, deleting it when it's needed, and it's always generated. So you don't have to back up the database or do anything cool like that. Does that make sense? Simple real-world example. This is basically like the conference room example. You go into a conference room and you're like, hi, I'm James. And then like Steve walks in. It's like, hi, Steve. Hi, Steve. I'm James. Steve, Steve, James. Then Julie comes in. Hey, Julie, Steve, James, Julie, Steve, Dave, so on. And that's basically what's happening. Everyone's exchanging data with each other. I think that was 3 people. But anyways, do you want to see more demos, or are you sick of this? What? I'm going to have them raise the mic, and I'm going to scream at you if you don't act a lot. I'm just going to kill these really quickly, but you can shut them down nicely if you want, which we won't do today. So I showed you some demos, blah, blah, blah. So now we're going to get and talk about the language, right? So this is the engine. This is what the engine does. But you want to describe what happens. This is actually kind of why I hate Kubernetes a little bit, because Kubernetes is like, here's this thing, it will do some stuff, but how do you like describe what you want to have to happen in Kubernetes? I don't know, blast some big YAML file data structure? It makes no sense. So this is what a language should be. a DSL, domain-specific language, a small thing. You want to elegantly describe what you want to do, and if you're trying to describe something bad that doesn't make sense, the language should stop you, right? So it should stop you from panics. You should not have no-pointer exceptions or any bad things that happen in languages. This is some computer science guy. I've never met him, but apparently he's nice. So some properties of the language. I've actually, unfortunately, had to build this language. It should be safe, it should be powerful, it should be easy to reason about. When you are building an infrastructure, and you have your load balancer, which is glued to Puppet, with a shell script, which is glued to Kubernetes, with a YAML file generator, you have all these different tools, how do you type check your whole system to ensure that it makes sense? You cannot do this. No one is doing this. So there's always bugs, and there's always, you can't write some sort of analysis tool that will check if the whole system as a whole makes sense. So if you want to have those tools like Kubernetes or something, it has to be lower in the stack, right, than what it is right now. Safe, powerful, here's some properties. So what I've actually built is I've built a functional reactive programming language, which is a DSL. I'm going to show you some examples of this. So here's the code I'm going to show you. Try and follow, we don't have built-in syntax highlighting yet, so this is just on my slides. I just have some variable y1, which equals date-time function plus a year. And then over here below that, kind of out of order, is we have this year, which is a big product of a bunch of stuff. And then we put a whole bunch of values into this struct, which is here. Oh wait, one of those values is load, and then we're going to put all that out into a file. That makes no sense. Let's see what we have. So I'm just going to run this, and hopefully we'll see what happens. So I'm going to run datetime3. Oops. And I'm just going to watch. Let me just remove these exchange files. So on the left, Mgmt is running, right? So it's doing its thing. It's running in real time. I don't know what's happening. And on the right, since the thing I asked Mgmt is to run all this code and set up one resource, which is a file, it's a little bit abstract, but just for demonstration purposes, this file is actually, we're just watching it. So we're just printing in a loop over and over again so you can actually see what's in the file. And you can see, actually, it's actually changing in real time. You have seconds, so you can see it's doing the math, it's printing out the year. And you can actually printing out the load, which seems to be changing about every 5 seconds. So all these variables, all these values, in real time are getting sucked up. Mgmt is doing some stuff, and then it's putting it out. So that output could be changing the number of resources, it could be doing all sorts of math, whatever you want. And just for showmanship, I've even made a VU resource. So if you look right here, if you're really quiet, but if you make a lot of noise, you can see it's in real time. So I actually have my computer microphone as one more data input in addition to air conditions, load, any other variable coming into Mgmt, and Mgmt is making real-time decisions based on those values. Is that cool? So if you think that's cool, we're going to be really quiet, and when I point to you, I want you to see how loud you can be to make this VU meter peak. All right, is that cool? You ready? 1, 2, 3. Cool? Believe. And you can try all this test at home. Think about the real-world implications of this. If you have like the microphone in your server room or your office and there's lots of screaming, maybe that's because people are fighting and you should like set all the systems read-only automatically until the sound has died down. So anyways, you'll have to use your imagination, but that's the idea. Can I move on or you want to see more? You want to see more? What? More. All right, that's my hackers. Who are my hackers? Let's hear my hackers. All right, thank you. Was that Julia? That was Julia. Okay. So now we're thinking about, so this paradigm of like real-time reactive languages is not something that I've invented. It's an existing thing. I have a sort of custom take on it. It's a bit different, but it's called functional reactive programming languages. So FRP in general. You don't have to be scared about functional programming. There's nothing scary. The normal functional languages like Haskell are super scary. This isn't. It's very simple. And the cool thing about having values which change over time is you can have historical values too. So let me see if I can just run this value. So I'm going to run this other option here. Just going to remove date time. I'm going to run my watch again. So what I've actually done, I'm actually running this code. So I have this variable that's set to date time, and then these values, ix 0, 1, 2, 3, and so on, they just look at that date time variable like you would normally use the variable, but we add this special syntax, curly brackets 0, curly brackets index 1, and so on. And these curly brackets, the language will automatically take the last value and the previous value and the value before that in time and just use them in that variables in this second. And then here we can just print them all out with a big printf. And as you see the time is going by, you can see the older values that were shown in that language. So not only can you program based on the conditions in this moment, but you can program logic based on previous historical conditions as well, right? So you can detect, is the load going up over time? Is the load going down over time? Any sort of things you want. Does that make sense? Okay, that's part one. Now we're going to make it complicated. I'm just going to kill this really quickly. So what's this? This is a photo I took myself on my lovely 2730 Classic Nokia phone. Thank you very much. What is it a photo of? Excuse the blurriness. What? Thermostat. That's good. Okay, this is actually my parents' thermostat. You can see it's in Celsius. On the internet, I found one in United States units, just is a little bit clearer, but unfortunately, I don't know what the numbers mean. And you basically set it, and it does some stuff. And thermostats, not Jonathan, have a property. So you can't answer because he's seen this talk before. Thermostats have an interesting property. Does anyone know what it is? Scream it out if you know it. Oh, that's very good. Kathleen is like probably the smartest speaker here, and she nailed it. Hysteresis. So what is hysteresis? Anyone know? So hysteresis is the following. Imagine we had a perfectly efficient heater in a room, okay? And you set the temperature to 20 Celsius, so it heats up the room really quickly. Boom, it's 20 Celsius. Then it turns off, and the cooling outside, because this is Quebec, cools really efficiently, so boom, it drops down a degree in a millisecond, and the heater clicks back on, so you're going to have the heater going really fast, right? Turns out this is bad for heaters. I don't know how the engineers build these things, but they don't like going on and off really quickly. So hysteresis allows you actually to have a delay based on a number of degrees or a time delay. There's different kinds of hysteresis that will say, okay, it's up to 20, I'm going to wait till you drop down past 18, and then I'm going to turn back on, go up to 20, and click off, and those sorts of things. Does that make sense? This is something you probably want if you have an autoscaler, because you don't want your autoscaler to like, start up VMs, oh, now there's too many, turn them off, and stuff like that. So I'm going to show you, you want to see a demo of this? Yes. What? Yes. Thank you, okay. Whew. What is this demo called? I forget. Oh, I remember what it's called, hysteresis. So I'm going to run this thing on the left. And on the right, I'm just going to run this big watch command. So I'm going to show you the code after, but basically the code is going to do some stuff, and then it's going to print out some debug info to a text file, just so we can see what's happening. It's a bit of an abstract concept because we don't really want to just put random data in text files for no use, but it's good for live demos. And what it's going to do in this watch loop, it's just going to run cat this file, and then it's going to run versh list, which is the command to list the VMs running on my laptop. Okay, and it's going to do that over and over again. And if you can see, what's happening is MGMT actually started up two VMs, MGMT1 and MGM2, MGMT1 and MGMT2. And what I've done is I'm also displaying the current load average on my machine and some threshold. So if the load on the machine gets too high, maybe that means there's too many VMs running here and we should push some off to another machine. Does that make sense? Yeah. So let's just fake that the VMs are doing a lot of work. Instead of mining Bitcoin and getting really rich off the venue's power, I'm just going to use like these commands, tree. And watch what happens when we hit 1.5. So my machine's going to get a little hot, and hopefully this should work. It's kind of an old, really ghetto laptop. So these are just commands that make the machine think it's doing lots of work, as if those VMs were running tasks. So it's going up there. Let's run one more yes. Watch what happens to those two VMs when we hit 1.5. Okay, at 1.0. The kernel actually updates this value every 5 seconds, so that's why you see it. 1.7, boom. And you see what happened? What happened to the second VM? It disappeared. So the autoscaler, or the code that is running in the MGMT language, said when we get above 1.5, turn off 1. But now watch what happens when we drop below. We drop below 1.5, and I've set a hysteresis for 10 seconds. So it did not reschedule that machine. It's waiting. 5 seconds go by, 10 seconds go by. Any second now. Let's see, is it working? Let's hope it didn't crash. It's about 10-second hysteresis. Libvirt is a little slow, and then it starts it back up again. Cool? Do you like that? You can clap. That's cool. I'll take a drink. So to do this, I can do this over and over again all day, but let's not heat up my machine. Play with this at home. I'm just going to kill this. This is just one example. This is just the silly example that I dreamt up for this demo. Your examples, your hysteresis, your real-time decision-making is all up to you. And instead of having like one custom API in Kubernetes or whatever for doing one thing, We instead give you a language, and you program it the way you want. And it's not complicated. It's easier than Python. It's easier than anything. I'll show you the code. You want to see the code? I don't usually show it, but it's all in GitHub. It's really simple. So there's no syntax highlighting. Here, let me just show this in Vim. It'll be a little bit bigger. It's really simple. So we just have, and the cool thing about these declarative languages, remember how things are out of order? The order doesn't actually matter. You should write things in the right order, but it doesn't really matter. So a lot of flexibility, because everything is very safe. So all we're really doing is I actually just have a simple hysteresis implementation, which I implemented, in 4 lines of code. We might actually make this a built-in, but for now it's just right there. And I have declaratively set up one VM, and then the second VM, it says the state. If there's load, shut it off. Otherwise, have it running. You don't, that's it. There's 5 lines of code in this logic. It's very simple, very powerful. And because it's a reactive real-time language, the code is always cleverly reevaluating itself and outputting new graphs of resources and dependencies to do all that work. Cool? So look at that on your own. I don't really want to show code, but something to think about. Okay? Some interesting properties. This is the boring stuff. We've got to sound sciencey so that the science people give us money. So the language and the engine, they're actually built into the same binary, but there's actually a logical API boundary separation. So what actually happens is the language is actually just running in real time and spitting out graphs, spitting out DAGs, directed acyclic graphs, to the engine. It says, please run this, now run this, I've changed my mind, run this, and does this every millisecond if it wants, every second, every hour, every day, it can change. There's actually, it's not really possible to cause a compile. If the code compiles, it's not possible for it to crash. There's a few exceptions based on hardware failing and runtime exceptions that are outside of our control. But basically, unless you have some really, really strange conditions, it's impossible to actually crash your code. So if it compiles, you're probably safe. I talked about this just briefly, but the code is actually a graph itself. So you should write it linearly the way it makes logical sense, but it can actually run in crazy orders. Just don't do this or you're insane. Variables are actually immutable. So if you were to do something like x equals 5 and then x equals 6, this would be a compile time error, because this is a class of bugs that is common in programs, mostly Python programs, and this language prevents them entirely. So that just stops bugs. And why do we care about stopping bugs? I don't know what the right answer is for that. It's just a canonical answer. Because bugs are bad? No. The reason it's important is because if this engine in this language is running 1,000 machines in your data center or across the world, you do not want an off-by-1 error or a variable reuse bug to take out a data center. And if you are not writing code that is sufficiently autonomous and clever to be able to manage all your data centers without human intervention, then you are doing it wrong. You're doing it wrong in the future. You will be a legacy company, and I will laugh at you from my MGMT cloud. But the good thing is, you like the cloud joke? I just threw that in. It's a new one. The good thing is you're going to learn all this stuff, and you're going to be the future data center hackers. Hysteresis, again, super powerful property. There's time-based hysteresis, like I showed you. There's also sequence-based hysteresis, where you looked at a certain number of previous values. Different things are possible. You program what you want. I talked about reactive variables. I haven't actually implemented this yet, but I plan to add reactive error conditions as well. So in the language itself, certain errors could happen, detect that resources have failed, and that could actually be input to the language as well. So based on if a resource fails or something runs an error or whatever, you actually then react and do something different, right? So you try and build everything in data center Hong Kong, but there's something really bad happening, so you, change to, Singapore or whatever. Cool? Say yes. Thank you. Please, if you don't interact, you don't get lunch. I'm an organizer, so I'm allowed to make these rules. This is not a democracy. So future work. How much time do I have? I'm going to go, okay, I got 10 minutes-ish. 5-10 minutes. Okay. So, 5, okay. Well, so I have this really cool scheduling demo if you want to see it, but only if Julia says I have time to show it. I'm just kidding, I'm putting you on the spot. Okay, I won't show this demo now. I have some other great demos, but I'm going to keep it short. This is a 30-minute talk, it's not the 45-minute version. But you can actually, just really quickly, I'll tell you what happens. You can actually describe in your sort of node declarations, when you think about how Puppet would say, hey, put this code here, put this code here. Instead, you can actually just have code that says, if you happen to be on this host name, do so-and-so. Or you can do things like have a schedule function, which is reactive, and it says, hey, if you're scheduling stuff, I want this body of code to run on 4 out of 8 servers present, or some other complex thing. And this is just inline code. You do it in one line of code, super easy. Won't show it to you today. So, how can you help? Do you guys and girls want to help? Yes. Thank you, Kenzie. So how can you help? You can use this. You can test this. It's all free software. Patch it, share it, document it, start it, blog it, tweet it, discuss it, hack on it with your friends if you want to write patches. Jonathan Gold here is an MGMT contributor. He's also looking for a job. So if you want to pay him to hack on MGMT, I think he's interested. Just hack on stuff. This is about hacking. There is some sad news. I know you've enjoyed my talk. I can see by your smiling faces. But we have to bring it down for a somber note. So I used to work at this big Linux company called Red Hat, who was funding my work. And it became sort of politically difficult because I was scaring the Ansible customers, and they were like, hey, we want MGMT. And Red Hat spent all this money on Ansible. It's a secret, so don't tell anyone. So I decided to leave Red Hat and work on MGMT on my own dollars. So I'm completely unemployed, hacking on this, spending my savings, and hopefully I can make some money doing MGMT and have people pay to support this before I run out of money. Because if I run out of money, I've got to go work for a big evil tech company or make this proprietary. Both of which suck, right? So I need money and stuff to help do this. So we need a home. If you want to help sponsor MGMT, if you want me to give these exciting talks and workshops at your company and help you implement this stuff and take over the cloud or the serverless or whatever the cool thing is, you let me know. I have a Patreon that I don't expect to make a lot of money with, but I just started it for fun. It helps me pay for stickers, which I'm going to give you today. So Purple Idea, I'm on Twitter, Purple Idea, Patreon as well, Purple Idea. Give me some money. I promise to make it worth your while. Let's just recap.
Answer. Now let me recap.
This is just Arthur Benjamin putting the cap back on his pen. It's not a very good joke. I should really stop using that one. We have an IRC channel, MGMT config on Freenode, so we're all hanging out there. There's a Twitter account if you're into tweeting and stuff, MGMT config as well. We have a mailing list, which is actually hosted by Red Hat for free, so why not? MGMT config list. It's mostly announcements about new versions and things, very quiet, like maybe one email a month, so probably worth signing up. There's some links. Purpleidea.com is the technical blog of James, one of the best websites on the internet, if I do say so myself. There's a GitHub page, purpleidea/MGMT. There's other videos of the engine and the language, and a bunch of blog articles and other things that other people have written, so you can find all that stuff. I'm Purple Idea at, oh, hang on a second. I don't work at Red Hat anymore. Let me just get rid of this. I don't work there. Oops. I knew there was going to be a typo. So you can email me at Gmail, at GitHub, Purple Idea, things like that. I don't have time for one last demo, so I'm sorry. So no more fire and other things. But I hope you like that. I'm basically out of time. You need to help me with one last thing. If you liked this talk, if you thought it was killer, you need to help me with a distributed denial of service of Julia, who is right here. So at some point, not necessarily right now, during the rest of the conference, just go up and be like, excuse me, Julia, can I ask you something? Yes, I really like James's talk. And if you all did that, that would be hilarious, right?